Hi, my name is Kaylee Burt, and this is my Physics 2 Lab 3 circuits. In this lab, I'll be investigating the behavior of electrical circuits using the principles of energy and current conservation, and providing insight into the practical applications of resistors and capacitors in electric systems. The purpose of my lab was to use the principles of energy conservation, loop rule, and current conservation, like I mentioned, to analyze the behavior of circuits, use multimeters to measure the actual values of potential current and potential differences, and then examine the function of capacitors in circuits in states of charge versus discharge. The results I got were that the loop and no rules are important for calculating measurements across circuits. The sum of potential differences across a circuit is 0 volts, and then in RC circuit, a bulb with more resistance takes longer to charge discharge. The physics principles I used for this lab: conservation of charge, and then Kirchhoff's loop rule, the sum of delta V around any closed circuit path is equal to 0 volts, and then node rule: in a steady state, the electron current entering one node is equal to the electron current leaving that node, so I in equals I out, and then we also use Ohm's rule: delta V equals current times resistance. And then the procedure for the series circuit, we determined that the current flowing through the circuit was this value here, which matched our prediction. And then we were asked to reverse the connection of the ammeter, which just gave us the same current, just a negative value. And then we connected the voltmeter to see the effects on the circuit, and it read 3 volts because the black probe was connected to the batteries, and that was the value, the voltage of the batteries. And the system is the circuit and its components, and the surroundings is everything else. And then moving on with the series circuits, we measured the potential differences across the circuit at each of the nodes, which are shown here. And then we got the sum was 0 volts, which matches the loop rule. And then once again, this was the current that we measured. And then we also completed the graph of potential versus position that we were given. Batteries raise the potential, and then wires have a negligible effect on the potential, and then the resistors lower the potential. And we were asked to attach the voltmeter and see why the ammeter doesn't change. We said that Kirchhoff's current law, the current doesn't change, and then we connected the voltmeter across the 100 ohm resistor again, and we said that there was no change in the ammeter. And then we were asked to replace the voltmeter with the ammeter in parallel to the 100 ohm resistor, and we said that the current gets split between the two paths. Since the ammeter has 0 resistance, the current avoids the resistor and thus creates a higher current, which is measured there. And then the resistance calculations, we just calculated the resistance of each component in the circuit, and then these calculated values align with the values we would expect each of the components of the circuit to have. And moving on to the RC circuit, what happens when batteries are connected to the bulb capacitor. We said as time passes, the light bulb becomes very bright and then dims until it turns off, and then that same thing happens when the bulb is connected directly to the capacitor. And then what happens to the current? In both scenarios, the current starts large and slowly over time flows and decreases to 0 amps. And then we were also asked to measure the time it takes for the capacitor to charge/discharge. And then using the 10 ohm bulb, these are the values that we got. We weren't able to discharge the capacitor with the 20 ohm bulb because we didn't have access to a working one, but I would predict that a bulb with more resistance would take longer time to charge and discharge. Then the predictions versus the model data. On similarities, the current that we predicted with the loop rule in the first series circuit was the same as the current that we measured in the circuit model, so that lined up. And then differences, the resistance values we calculated using our electric potential obtained from the model might not have been 100% accurate, as they were close to the resistance values we predicted, but not exactly at around them a little bit. And then the values that we predicted assumed for the time it takes the capacitor to charge/discharge with different bulbs were different than the values that we obtained. We also weren't able to obtain the time measurements for the 20 ohm bulb, that's why. And then the potential sources of error. Real world model could have been less accurate due to human error and the error/faultiness of some of the equipment that we were using. We could have run more trials for more accurate results with discharging the capacitor, and we could have performed a part of the experiment like incorrectly or misunderstood the instructions. And then what if you charge a capacitor with no resistance? How quickly in the ideal model would the capacitor reach full charge, and then would this happen in real life? In ideal model, if you charge a capacitor with no resistor, the capacitor would theoretically reach full charge almost instantaneously. However, in real life, the capacitor will not reach full charge instantly. The other components in the circuit have small resistance, which limits the current. And then the time it takes to charge the capacitor when connected directly to the battery is, like I said, longer than like the ideal world prediction. It'll have a curve that's much closer to the real world exponential charging curve. Thank you.